Dear students, after studying this module, you shall be able to understand why aromatic compounds undergo electrophilic aromatic substitution. You will also know about the mechanism of electrophilic aromatic substitution and Arenium ion or the VLAN intermediate which is involved in the same. You will also understand the isolation of the Arenium ion intermediate as a proof of the Arenium ion mechanism which is involved in this electrophilic substitution. We will also learn about the orientation and reactivity of benzene and the related aromatic compounds towards electrophilic aromatic substitution, and we will also study about the energy profiles or the free energy diagrams which are associated with the electrophilic aromatic substitution. Now students, let us begin with the introduction of this topic, that is the electrophilic aromatic substitution. Now in the previous modules we have taught you that aromatic compounds are stabilized by the aromatic stabilization energy. Due to this stabilization, normal SN2 reactions observed with alkanes do not occur with aromatic compounds. That is, SN2 reactions, they will never occur on the sp2 hybridized carbons of benzene or related aromatic compounds. Now, for an example, you will see here that bromobenzene, when reacted with alcoholic salt, that is the methyl and the alcohol of sodium, you will not observe any reaction with that. In addition students, the double bonds of the aromatic group do not behave similar to alkene reactions as well. Now you may be wondering, okay, if the aromatic compounds do not give you any SN2 type of reactions, but they are having the double bonds, that means they must be giving the reactions associated with the alkenes. However, that is also not observed. Now you can see the reaction of benzene here with an acid, then again no reaction is observed. While aromatic compounds do not react through addition reactions. So this is the basic outcome of these two things which I have told you. That means they neither undergo the SN2 substitution or they will not undergo the addition reaction which is observed in alkenes. Thus, the most accessible feature of benzene or the aromatic compound is the concentration of negative charge above and below the plane of the ring of carbon atoms. What happens with this is that this charge shields the ring carbon atoms from the attack of the nucleophilic reagents, and this observably promotes the attack of cations or the electron deficient species, that is electrophilic reagents, onto the aromatic ring. This is in contrast to most substitutions in aliphatic chemistry that we have taught you in the previous modules, in which the electron rich nucleophile attacks the electron deficient carbon. Now you can see here we have displayed the concentration of charges, how it is done in aromatics, that is the plane of the ring and below the plane of the ring, and how the charge is delocalized over all the carbon atoms which are sp2 hybridized. So this is the feature of benzene which actually makes it susceptible to most of the reactions, that is electrophilic aromatic substitution reactions. Now students, we come to the next point, that is the attacking nucleophile is a positive ion. So the attacking electrophile students is a positive ion or positive end of a dipole or an induced dipole. So after the reaction, the leaving group must depart without its electrons. The most common departing group students in case of aromatic compounds is a hydrogen ion, that is hydrogen cation, that is H plus ion. Now we have stated here in this figure various examples of electrophilic aromatic substitution reactions. Now students, notice here that what kind of reactions or electrophilic aromatic substitution reactions does the benzene undergo. First one you can see here is the halogenation, second one is a nitration, third one is a sulfonation, then is the alkylation and acylation respectively. Now in all of them you can see, if a hydrogen cation does not leave as a departing group, then we would not have these products. So an essential feature is the attack of the electrophile onto the benzene ring and the departure of the leaving group as a positive ion. Now let us come to the next feature of electrophilic aromatic substitution, that is the Arenium ion mechanism and energy profile diagrams. Now let us come down to the steps which are involved in the Arenium ion mechanism. Now what is an Arenium ion? Arenium ion is basically an intermediate which is involved in the electrophilic aromatic substitution. Now the mechanism of aromatic electrophilic substitution is known as the Arenium ion mechanism after the intermediate which is basically formed in this reaction. And this is having two main steps. The initial step, students, is the attack of an electrophile creating a resonance stabilized carbocation or intermediate called the Arenium ion, as already stated by me, which is also known as VLAN intermediate or a sigma complex. Although the VLAN intermediate or a sigma complex, which is now popularly known as Arenium ion, is stabilized by resonance with the charge dispersal all over the carbon atoms ortho or para to the site of attachment of the electrophile. This site is accompanied by the loss of aromaticity, so the energy of activation is very high in this case. Now students, you can see here, when an electrophile attacks the benzene ring, what happens? Because it is short of electrons and it is electron loving, that means it will take up the electrons, the charge on the ring, thus it will make the ring electron deficient. So whatever charge is left on the ring will be delocalized all across the ring, and thus a resonance stabilized carbocation is formed. Although students, in this carbocation intermediate, you can see that the aromaticity is lost, but still it is stabilized by resonance of the other two charges of the double bonds which are left. Now students, I would like to tell you that this first step is the rate determining step, and it is a slow step of the reaction because of the disruption of aromaticity in this step. Now coming over to step number 2. In this second step, students, the leaving group basically departs. What has been there in the carbocation, as you can see, to regain the aromaticity. Now this step leads to the regeneration of aromatic stabilization. The second step is nearly always faster than the first one, making the first one the rate determining step, and the reaction is second order. Now you can see in this reaction, that is the second step of the reaction, how the hydrogen cation is basically leaving and the aromaticity is being regained. Thus we again form the same system, but now the electrophile is attached onto the ring, not the hydrogen, because it has left the ring. Now note students, there is some resemblance of this mechanism to the attack of nucleophiles on the carbonyls of esters or amides to give you a tetrahedral intermediate which is formed, except that the charges are reversed. If the electrophilic species is not an ion but a molecule with a polarized covalent bond, the product must have a negative charge unless it is part of a dipole, with its pair of electron is broken off somewhere in the process, as in the conversion of A to B. Now as you can see here, what is A and what is B, how it is different from the nucleophilic substitution in case of carbonyls and esters. Note that when the aromatic ring attacks X, Z may be lost directly to give you the B. Now you see here the difference when the attacking electrophile is a molecule instead of an ion. What is the difference? Now let us come to the topic of energy profile diagram of the Arenium ion mechanism of electrophilic aromatic substitution. Now we have stated that the first step is a slow step and is a rate determining step. However, second step is generally more faster than the first step. Now as you can see here, it's a slow step and thus its free energy in the diagram, and second step is a fast step. So briefly, I'll just put the points. The energy diagram of this reaction shows that step 1 is highly endothermic and thus it will have a large free energy, that means delta G dash. The first step requires the loss of aromaticity of the very stable benzene ring, which is highly unfavorable at that time for the system. The first step, being a slow step, is rate determining. Now let us come down to observation of step 2 in this diagram. Step 2 is highly exothermic because regain of aromaticity is taking place. So it has a small delta G, as you can see here in this figure. The ring, it regains the aromatic stabilization, which is a highly favorable process. Now you can understand how the slope is basically differing in this diagram of the free energy, which is displayed here. Now students, I will tell you briefly about the generation of electrophiles. We have learnt about the steps which is involved in electrophilic aromatic substitution. We have learnt about the energy profile diagram, where it is fast and where it is slow steps are there in this reaction. And we have also learned about regain and loss of aromaticity in this reaction. But now I would like to take up how the generation of electrophiles takes place. The electrophiles can be generated in various ways in the examples that I will be discussing. Now as you can see, the reaction name here is nitration. Considering this, like say we are nitrating the benzene ring, so what it will require? It will require H2SO4 and HNO3. Why? Because H2SO4 helps in the generation of nitronium ion, which is the needed electrophile in this case. Now if you see the bromination, which is part of halogenation of benzene ring, in this case FeBr3, that is tribromo iron, this compound, this helps in the generation of the Br plus as an electrophile. Let us come down to the discussion of Friedel-Crafts alkylation. Here again, with the help of a Lewis acid like aluminium chloride, this R plus cation is generated, which behaves as an electrophile to attack the aromatic system. In case of Friedel-Crafts acylation, students, again this RCOCl group, that is the chloride, carbonyl chloride is taken up, and again with the help of a Lewis acid, you will see the formation of the RCO plus cation, which is actually the electrophile in this case, that is the Friedel-Crafts acylation. Now comes the very famous Willesmer-Haag formylation. Now again, here the electrophile is generated with the help of POCl3, and this electrophile is here in front of you, where you can see the positive charge on the nitrogen atom. Again in mercuration, this is the ACO minus and the HGOAC, this is the ion where the electrophile is generated. In deuteration, instead of H plus, the D plus basically attacks the benzene ring, and you can see how the D plus is generated and the DSO4 minus is the corresponding anion. In this sulfonation, students, SO3 is basically the electrophile which attacks the aromatic system and gives rise to the electrophilic aromatic substituted product. Now students, after having studied the generation of electrophiles and the mechanism and the Arenium ion formation, I will now tell you about what is the evidence that the scientists have gained to be actually sure that the Arenium ion is formed in case of electrophilic aromatic substitution. Now the topic is evidence of the formation of Arenium ion mechanism. The evidence for the Arenium ion mechanism is basically of two kinds. First evidence is isotope effects. If the hydrogen departs before the arrival of the electrophile, that is as in case of SE1 mechanism, or if the arrival and departure are simultaneous, there should be a substantial isotope effect. That is, deuterated substrates should undergo substitution more slowly than non-deuterated compounds because of the mass law that I have already told you, because deuterium is heavier than hydrogen, because in each case the CH bond is broken in the rate determining slow step. However, students, if you notice, then in the Arenium ion mechanism, the CH bond is not at all broken in the rate determining step. It is actually broken in the second faster step. There is a gain in the aromaticity or the regain of the aromaticity. So, no isotope effect should be found. Many such studies have been carried out, and in most cases, especially in the case of nitration reaction, there is no isotope effect. This result is incompatible with either SE1 mechanism or the simultaneous mechanism that I was talking about. However, in many instances, students, isotope effects have been found. Since the values are generally much lower than expected from either the SE1 mechanism or the simultaneous reaction mechanism. For example, 1 to 3 is the value for Kh by Kd instead of 6 to 7. So, there must be another explanation for this. For the case where hydrogen is the leaving group, Arenium ion mechanism can be summarized as, now this I have already told you, first is the attack of electrophile, second step is a faster step, in that the hydrogen leaves. So, the small isotope effects found out most likely arise from the reversibility of step 1, which is the slow step, by a partitioning effect. The rate at which ARHY plus, which is the intermediate which is formed, reverts to the original system, that is the original aromatic system, which has not undergone the electrophilic aromatic substitution, should be essentially the same as that in ARDY plus, that means which is substituted with deuterium, or the tritium, that is AR, that is the phenyl TY plus, T is the tritium ion, and reverts to ARD or ART, that is the deuterated benzene or the tritiated benzene, since ARH is not cleaving. However, ARHY should go to ARY faster than ARDY plus or ARTY plus, because obviously the mass of deuterium and tritium is higher than that of hydrogen. Since the ARH bond is broken in this step, now if K2 is greater than K minus 1, that is the reverse reaction, this does not matter, since a large majority of intermediates basically go to the product formation. The rate is determined only by the slow step, as you have already read in kinetics, that is K21 and the concentration of the benzene divided by and the concentration of the Y plus, that is the electrophile. And no isotope effect is predicted. However, if in case when K2 is less than or equal to K minus 1, reversion to starting material is important and should be taken into consideration. If K2 for ARDY plus, that is the deuterated Arenium ion or the tritiated Arenium ion, is less than K2 for ARHY plus, that is only the hydrogen containing Arenium ion, but K minus 1 is the same, then a large proportion of the deuterated Arenium ion reverts to starting compounds. That is K2 divided by K minus 1, that is the partition factor for the deuterated Arenium ion is less than that of the hydrogen containing Arenium ion. Now consequently, the reaction is slower for the deuterated benzene, then only the single deuterated benzene, then for the benzene, and a isotope effect is observed in this case. Now this is the evidence when you talk of the isotope effects, when you replace the hydrogen with deuterium or tritium. The next evidence, students, is the isolation of Arenium ion intermediates. The isolation of Arenium ions, in many cases, it provides for a very strong evidence for Arenium ion mechanism, because here instead of the isotopes and labeling and depending on the reversibility of the first step, you are actually being able to isolate the Arenium ion itself, and then you can study it, and that is the clear proof that Arenium ion mechanism does occur. When this compound was heated, the normal substitution product obviously was obtained. Even the simplest of such ion, that is the benzonium ion, has been prepared in HF, SbF, SO2, ClF, SO2, F2 at minus 134 degrees Celsius, where it could be studied spectrally. Now you can see, by actually restricting the moment in this compound of the Arenium ion, the scientists have been able to isolate the Arenium ions, and they have studied the Arenium ions spectrally, and this provides for a great evidence of the favor of the Arenium ion mechanism. Now we take up orientation and reactivity. When an electrophilic substitution reaction is performed on a mono-substituted benzene, the new group may be directed primarily to the ortho, meta or para positions. Although sometimes it is possible that a fourth type of substitution may be encountered, that is ipso substitution, which is a special case of electrophilic aromatic substitution, where the leaving group is not hydrogen but the original substituent itself. Now here you can see we have shown the ortho, para and meta substitution, and also the ipso substitution, where the R group has to leave itself for the incoming electrophile to be accommodated. Note students that the substitution may be slower or faster than benzene itself. Thus, formation of 4 possible intermediates is dependent not on the thermodynamic stability of the products, but on the activation energy necessary to form the 4 intermediates. Consider the Hammond postulate in this case. We assume that the geometry of the transition state also resembles that of the intermediate, and that anything that increases the stability of the intermediate will also lower the activation energy necessary to attain the same. Now here you can see how the energy for Arenium ion is minimum and ortho deactivating is there at the highest, or the para deactivating is also at the same place. Next to it is the meta deactivating group. So the group already on the ring determines which position the new group or the new incoming electrophile will take, and whether the reaction will be slower or faster than the benzene itself. Groups that increase the reaction rate are called activating, and those that slow it down are known as deactivating groups. So the groups often seen here as R or Z, according to their influence on both reactivity and orientation, are classified into different categories. 2 properties of these groups have a major influence, namely the inductive effects and the resonance, sometimes known as the older form the mesomeric effect, often depicted as RE or M effects. So students, the groups here fall into categories. First is the O minus, primary, secondary and tertiary amines, hydroxyl, ether, NHCOR and the ester OCOR. That is the first category. Second category is the NO2, that is the nitro, the cyano, sulfonic acid, CHO, COR, the carboxylic acid and the amides. Third category is the alkyl groups. Fourth is the carboxylic acid. Fifth one is the salts of amines or alkyl amines and the trihalogen carbons, that is CCl3 or CF3, and the final category is the halogens itself, that is fluorine, chlorine, bromine and iodine. Now these categories have different activating and deactivating effects on the ring, and they decide where the incoming electrophile will be, and they will also decide the activation energy which is involved in step 1 and the step 2 of the mechanism. Now here you can see how the incoming electrophile is placed on the ortho, meta and para position if already one substituent in the form of R or Z depicted is there on the ring. Now students, I will now take up 6 common electrophilic aromatic substitutions and It will briefly give you a preview of what you are going to study in the next modules, where we will actually discuss in detail what is the effect of each of this category on the benzene ring or on the incoming electrophile when the second electrophilic aromatic substitution is carried out. First, I would like to discuss here the halogenation. This is done by replacing hydrogen with a bromine or a chlorine atom generally. Both processes, bromination or chlorination, they require a Lewis acid for the generation of electrophile. Now this accepts a pair of electrons to create a permanent dipole of the Br-Br bond or the Cl-Cl bond in which they naturally exist. This dipole allows the bromine or chloride to have a formal positive charge and therefore allows the generation of electrophile, and it also allows it to be electrophilic enough to overcome the activation energy caused by the loss of aromaticity in the step 1 in the benzene ring. Now consider the chlorination of nitrobenzene. Now students, briefly I will tell you here that nitro group is an electron deactivating group for the benzene ring, and this gives rise to a meta substituted product. Now second example is the nitration. This happens by the replacement of a hydrogen with a nitro group. Nitration process requires the presence of sulfuric acid as a catalyst to generate the nitronium ion, which is an electrophile over here. Just like we had to take extra steps to create electrophile in case of halogenation, that is bromination and chlorination, and we must here use the sulfuric acid to result the same electrophile, which is the nitronium ion. The nitronium ion can then proceed as a general electrophilic aromatic substitution reaction. Nitration of toluene here is an example that I will take, and it will give you a para product. And let me tell you here, we have taken this as an example of alkyl groups from the categories, and that is a ortho and para directing group. So the incoming electrophile, that is a nitronium ion, it will come onto the majorly to the para position. Also in some quantities ortho product will also be formed. Next student comes the sulfonation. This occurs by replacing a hydrogen atom with a sulfonic acid, that is SO3. The sulfonation process is quite similar to nitration because students, in general, we create an electrophile by protonating the SO3 with H2SO4 to make it a stronger electrophile. The mechanism can then proceed as a normal electrophilic aromatic substitution reaction. The sulfonation of acetophenone I have taken as an example here. This will also give you a meta substituted product because here the COCH3 group is an electron withdrawing group. Next comes the Friedel-Crafts Alkylation. Now this was discovered by scientists Friedel and Kraft, so the reactions are named after them. Friedel-Crafts Alkylation occurs by replacing a hydrogen atom with an acyl group, that is the RCO group. In Friedel-Crafts Alkylation, we form the acylium ion, which is the electrophile in this reaction, by using a lone pair of the chlorine, that is of the CH3COCl for an example, open the octet of the aluminium of the AlCl3, which is basically a Lewis acid and helps in generation of the electrophile in this case. As a result, the chlorine atom bond is weakened and Cl plus AlCl3 leaves, that is AlCl4 minus leaves. The acylium ion acts as an electrophile in the electrophilic aromatic substitution mechanism. The hydroxyl group here is an ortho-para directing group, and thus a para substituted product is formed henceforth. Now here students, we have taken the example of phenol. Now you can see phenol is a ortho-para directing group, and I will tell you here, and the details will be discussed in the modules to come, and obviously major product is para and some of the ortho product is also formed. The fifth example is again Friedel-Crafts Alkylation after the name of the scientist. Friedel-Crafts Alkylation occurs by replacing with an hydrogen atom with an alkyl group. In Friedel-Crafts Alkylation, we use a lone pair of chlorine of the say RCl, here it is methyl chloride, to open octet of aluminium chloride, which is the Lewis acid. As a result, AlCl4- it leaves. The cation generated, that is the R plus cation, it acts as an electrophile in the electrophilic aromatic substitution. Alkyl group here is an ortho-para-directing group in toluene, which we have taken as an example. Thus, a para-substituted product is formed henceforth. Next example, students, is the diazotization of primary amine. In this reaction, we react an acid like H3O plus with NO2- to form a nitrosonium ion, that is NO+, which behaves as an electrophile. Then we form the NN bond with the electrophilic attack of nitrosonium cation to form the aniline. Then through a series of protonation and deprotonation steps by water, that is the proton shuttle we call it, a diazonium cation is formed. Now you can see here this how a series of the proton shuttle is taking place, and finally the attack of electrophile takes place. Now students, these conclusions of attack of the particular group leading it to ortho or para or the meta product or the ipso product are correct as far as they go, but they do not lead to the proper results in all the cases. In many cases, there is a resonance interaction between the group which is already present and the ring. This also affects the relative stability of the same compound, and in some cases the same direction as the field effect, in others differently. So students, in most of the cases this is true, but not for all cases, as you know that chemistry is full of surprises and each reaction might give you a different product sometimes. Now students, let us summarize this module. In this module students, we have taught you that SN2 reactions observed generally with alkanes do not occur with aromatic compounds, as they are stabilized by aromatic stabilization energy. The concentration of negative charge on the plane of the ring carbon atoms makes the aromatic systems susceptible to attack by electrophiles. Arenium ion or the VLAN intermediate or the sigma complex is the name of the intermediate which is involved in this reaction, and Arenium ion mechanism has two main steps. Now we have taught you that the first step is slow and is a rate determining step, and it involves the attack of electrophile and loss of aromaticity, although this loss of aromaticity compound, that is the carbocation which is generated, or the Arenium ion, is resonance stabilized. The second step students is the departure of the leaving group, again leading to the regeneration of or the regain of the aromaticity. The first step is highly endothermic, while the second step is highly exothermic. We also told you that as a proof of the Arenium ion mechanism, there is an isotope effect and the isolation of the Arenium ion itself, which can be studied spectrally to analyze and make a proof for Arenium ion mechanism itself. And we told you that when an electrophilic substitution reaction is performed on already substituted or mono-substituted benzene rings, the new group may be directed to the ortho, meta or para positions, or sometimes the ipso attacked product are also formed. That is a special case of substitution where the group itself has to leave and make way for the electrophile itself. Now the group already on the ring, that determines whether the incoming electrophile will go in ortho, meta or para substituted product, or whether the reaction will be slow or fast. Groups that increase the reaction rate are activating, which decrease the reaction rate are deactivating or the meta directing. The activating ones are ortho and para directing. In many cases students, we have taught you that there is a resonance interaction between the Z group which is already present on the mono-substituted benzene ring. This also affects the relative stability. In some cases in the same direction as the field, in some cases it attacks differently. So we have to decide in some cases what kind of product is formed apart from the knowledge that we already have.